Space, the final frontier. These are the voyages of the JWST.
Sadie, what are you doing?
Impersonating James T. Kirk?
No, I mean, why are you talking about Star Trek in the first place?
Well, it's a new season of Carry the Two, so I wanted to kick us off with a bang.
Okay, but why don't we start by introducing who we are and reminding everyone what we do on Carry the Two?
Okay. I'm Sadie Witkowski.
And I'm Ian Martin.
And you're listening to Carry the Two, a podcast from the Institute for Mathematical and Statistical Innovation, aka IMSI.
This is the podcast where Sadie and I talk about the real-world applications of mathematical and statistical research.
We might seem like an odd couple to tackle these topics. I'm a cognitive neuroscientist, and Ian is a high school choir teacher. But it turns out you don't need a degree in mathematics or statistics to know how to apply them to the world around you.
So, now that we've gotten that out of the way, let's go back to the JW whatever.
JWST, also known as the James Webb Space Telescope. It launched in December of 2021 after over 10 years of development. And today's guest, Mike Menzel, knows all about it.
I've been working this job for about 25 years now, so I've seen it from womb to tomb.
Mike Menzel is the Mission Systems Engineer for the James Webb Space Telescope, aka JWST, and he's a bit of a character.
Tell me more.
You know, we take long flights, flying back and forth all the time, and they'll do Sudoku, they'll do crossword puzzles. I usually bring a calculus book with me or a physics book. Before the flight starts, I pick out about 3 problems, and I get really upset if I don't get the answer to those 3 problems by the end of the flight.
Oh, I actually love that. I know it's not the same, but before long flights, I like to download crossword puzzles. But also nerd alert, I guess, or nerd recognizes nerd. I don't know.
Nerd recognizes nerd. Yeah. I like it. Oh, yeah. Mike is an unabashed math nerd. He's previously worked on the other major telescope that you probably have heard of.
A lot of us who worked Hubble ended up, transitioning to James Webb. We knew where the skeletons in the closet were. We knew what we want to fix.
The Hubble is the telescope that's been orbiting Earth for several decades, right?
Right. Hubble has been a real workhorse for so many years, and it's been serviced by astronauts several times just to keep it up and functioning. But when NASA had the chance to put an even more powerful tool into space with JWST, well, they really wanted to make sure that they got it right.
So is JWST just Hubble 2.0, or is it fundamentally different in some way?
Well, there are actually a bunch of differences in the engineering that was required to get JWST into space and functioning to begin with, but I'll let Mike explain the differences in the telescope portion.
So it's a combination of the size of our telescope and the fact that it's infrared and the fact that it's out of the atmosphere. All those things make James Webb a pretty powerful thing for seeing very, very faint infrared sources.
And Hubble isn't infrared? Why do we care if we can see infrared to begin with?
Oh, we'll get there, I promise. But the main reason I wanted to talk to Mike was because he was the lead engineer tasked with figuring out how to get the JWST into space and unfolded so that it could actually start taking pictures.
Unfolded?
Oh, yeah. This is part of why JWST was such an engineering feat.
When you look at the telescopes that were flown before Webb, they're all designed, they all actually look similar, and they look similar for a good reason. They're all designed to not change. They're stiff, they're rigid. The whole design paradigm is make them so stiff that launch can't upset them, right? Well, James Webb is a whole different bird. James Webb has to be folded up, and it's you build this great telescope, you test it, you align it, you show it works on the ground, and then you bust it up. You bust it up, you fold it up, and you have to rebuild it on orbit. So that was a different animal for a lot of us, and it was really challenging.
So basically, most satellites are these solid cubes with minimal moving parts. You really don't want too many moving parts because each one then becomes a point of potential failure.
So why the big change with JWST?
So you know how telescopes use these huge concave mirrors to gather light and create images?
I didn't know that, but go on.
Well, JWST doesn't just have one mirror, but a series of 18 hexagonal mirrors to focus infrared light from crazy distant light sources.
So they had to unfold the mirrors?
Yes, and this massive sail-looking contraption that we really want to talk about, the solar shield. Basically, because the mirror was so huge to collect really weak, distant light, we needed a way to protect it from our own sun.
Oh, so the solar shield makes it so that the light from our sun doesn't outshine distant objects we're trying to observe.
And if you watch the video, which you can check out in the show notes, you can actually see the shield unfurling.
For those of us who are not looking at it right now, could you explain what it looks like?
Well, I initially assumed that the satellite shield and all the other parts folded up like an origami project. Mike quickly disabused me of that assumption.
And, they call it origami, but that really doesn't do it justice. Sometimes I like calling it like packing a parachute. You see, the thing that was, people can fold up satellites and deploy them on orbit. It's not something you like to do, but we know how to do it when they're rigid. But when you're building things that are deterministic, like stiff, rigid beams that are on hinges that can latch, you know how they act. But Webb and that big tennis court sized sun shield, that things that are floppity, things that can move places you don't want them to, that are intrinsically undeterministic, that's a pain. And you trying to control that in 0G takes some thoughts. You see the animations of the thing unfolding. And I used to tell the college kids this. If you think tennis court size sheets slide over each other like satin sheets in 0G, you're kidding yourself, right? And if you think all the pulleys and cables that we have on that don't tend to go to places you don't want them to go and snag, you're kidding yourself. So it was that aspect of the deployment that made it even harder. And that's where it's a little different than origami, because origami, you almost have stiff pieces of paper that you're folding along lines. And no, it wasn't quite like that. It was a little more difficult.
Thank God they're not fitted sheets, am I right?
I know, it's wild. 5 tennis court sized sheets of this material just stacked on each other to really block the sun's light. And we often talk about the solar shield as being one single sheet that has to be carefully stretched out, but with multiple membranes, as Mike calls them, they had to be really carefully deployed without tangling or getting caught.
I guess it would be too expensive to send an astronaut up to detangle it?
Well, JWST is actually in an orbit so distant from us that we couldn't even do that if we needed to.
It's not just orbiting the Earth like Hubble?
Nope. The JWST is actually located at the second Lagrange point, usually referred to as L2. But if you're not a fan of the Expanse book series, this is probably a new term for you.
Yeah, I'm not much of a sci-fi reader. Well, that is unless there's a queer romance involved.
So a Lagrange point is a position where the gravitational pull of 2 large masses precisely equals the centripetal force required for a small object to move with them. Essentially, it describes a point in space where 2 sources of gravitational pull can work together to keep a satellite in stable orbit. In this case, the Earth and the Sun. Although it was long before we were putting telescopes into space that mathematician Lagrange discovered these 5 points. It was way back in 1772 as a solution for the 3-body problem.
So there are 5 stable points between the Sun and the Earth?
Yep. Although, technically, 3 of the points are unstable and 2 are stable, but for the JWST, all you need to know is that they place the telescope in a high orbit at Lagrange point 2, which gives it a pretty stable orbit around the Sun, staying on the far side of the Earth. So by placing it at L2, the combined centripetal forces keep it orbiting the Sun while also keeping pace with our Earth. All this is to say, this telescope is much further away from Earth than Hubble, a whopping 1.5 million kilometers compared to Hubble's measly 570.
Okay, so if the JWST is super far away and can't be serviced if something goes wrong, how could they even know if the sun shield would deploy properly? Could they test it?
In the initial tests of single membranes, remember the sun shield is 5 individual membranes, but we did actually build pools down in I think it was Alabama, and we wanted to make sure that we understood the zero G shape of the membranes. And to do that, they actually did float them on. I think the pools that they made were almost kiddie pools, like about a foot a foot deep or so, but we did do that. But that was for individual layers. Once they're put on the assembly and they're tensioned the way we tension them in space, then we couldn't do that anymore.
LOL, I'm just imagining NASA scientists trying to fold massive fitted sheets in a plastic kiddie pool.
But with lots of math.
Obviously.
Because this is all being done by a robotic system of pulleys and lines, of rigging and stuff like that.
For instance, there's several lengths of cable that actually go through what look like soda straws, because those soda straws will keep the cables, when they're slack, from going in places that you don't want them to. We had to readjust where some of the pulleys were for the same reason, just to make sure that whatever slack we had in the line could be managed.
Besides having the world's longest kiddie pool, did they also have to create crazy complex mathematical models of how all the lines were pulling out the solar shield layers? It seems like a lot of variables to contend with.
Because it would be so computationally intensive, they didn't start with the math. Instead, they used real-world physical models and spotted the problems from there. Then they used math to help find solutions to areas where the system ended up snarled. Take the lines used to pull out the solar shield layers, for example.
We wanted to make sure that that the lines would never snag or tangle. So we would take the locus of all the positions that those lines could be in, look at their envelopes and make sure there was nothing in that. And for the way we restrained them, a lot of times that came down to ellipses. They almost took an elliptical shape because of the way they were constrained. So we did look at the math of where those lines could get and make sure there was nothing there that they could snag on, that type of thing. But for the most part, because we're so non-deterministic, the best thing we did was build a full-scale model of the sun shield and practice packing it and practice deploying it.
What does he mean by non-deterministic?
Basically, it means that there are some physical systems that have so many interconnected wiggly parts that the lightest perturbation, or bump, will change their expected behavior. And so every time you run the experiment, you get a different result, and often not the result you wanted. So Mike and his team had to reduce the effects of this non-determinism through trial and error as they improved their design. Because in space, they were only going to have one chance to get it right.
We used the full-scale test model to find the problems. Once we identified the problem areas, that's when we applied the math. So, if you try to rely on the math by itself to identify the problem areas, I think that the best way I could say this, being that it's non-deterministic, you could almost probably, I suppose, a professor could invoke chaos theory or something. But you wouldn't rely on theoretical math to find the problems. You'd rely on, hey, build the thing and look at here are the problem areas, then apply the math locally to come up with your solutions.
So basically, they use math as a matter of last resort to solve issues that come up with the design?
Yeah, and since they're applying math to problems as they crop up, you get all sorts of fields of mathematics research that are vital.
What kinds of math, like what kinds of theory or fields of math were you using for this kind of work?
Well, I wrote that down. Just about, you name it, we've used it.
I don't even know that I could name that many kinds of math.
Oh, me neither. I had to ask Mike for some specific examples of mathematical tools that they used in the sun shield.
When you want to figure out the deployed shape of the sun shield under the tension field, you could get into some really, really advanced type of math, differential geometry, almost bordering on topology for some of this. And, the way that tension field distributes. Now, most of the engineers I work with don't really engage in that kind of math, so they'll just build a finite element model and see what the computer tells them to do, right? But you can certainly invoke some theoretical math. We knew that when we tensioned the shape of that sun shield, its perimeter would be a catenary. And for those that have taken, some college math, they know what a catenary is. It would almost look like the lines or the cords on a suspension bridge. which theoretically that shape is a catenary. And that's what the shape of that, the perimeter of the sun shield look like. The actual shape of the surface, you could start to invoke Gaussian surface theory and differential geometry for that kind of thing.
Oh, yeah, that sounds like a lot of math we didn't even come close to touching in high school. At least I got catenary, I think. That's the idealized shape of like a rope hanging between two pylons or something, yeah?
Exactly. It's the bow in a slack line between 2 points in a uniform gravitational field. But I think the bigger point here is that Mike and his colleagues at NASA really just treat math as another tool in their toolbox to help them build the best satellite telescope possible.
I can get behind that. Not that anyone asked, but I can.
Actually, Mike said something to me that reminded me of my college physics professor's love of Fermi problems.
I'm somebody who loves, I'm not a computer geek in any way, shape, or form, but I believe in hand calculations. And I believe that, you can, if I can't get a zeroth order prediction of what that computer's telling me, I either get myself educated by the expert or I start wondering what's wrong with that computer. And I'm a firm believer that, I may not be able to do finite element models in my head, but I can do some hand calcs and get it to within 10 to 20% of the answer. And if I'm farther out than that, then either I need the education or that computer's wrong.
I never thought of myself as a math person or even a physics person, but for my college liberal arts physics class, we had weekly problem sets that always included a Fermi problem.
Yeah, you still haven't explained what that is.
Fermi was a physicist who worked on the Manhattan Project, and he was all about taking the information you had readily available and using it to calculate or make estimates. Like going from knowing that most hamburgers are a quarter pound of beef to then trying to estimate how many cows we eat as burgers in the US each year. Turns out you can get within the right order of magnitude just by using the small things you already know. I always thought these problems were kind of neat. I mean, shout out to Austin Gleason.
Well, as long as you're not going to ask me to calculate when two trains moving at different speeds are going to intersect,
Yeah, no, you're safe from me. Let's get back to the topic at hand, JWST and the solar shield. Now that we've talked through some of the engineering and the math behind building the telescope, let's take a quick break.
Next up, the launch of JWST and all the cool space photos we've already gotten since it was sent up.
If you're getting a lot out of the important research shared on our show, there's another University of Chicago Podcast Network show that you should check out. It's called Big Brains. Big Brains brings you the engaging stories behind the pioneering research and pivotal breakthroughs reshaping our world. Change how you see the world through research and keep up with the latest academic thinking with Big Brains, part of the award-winning University of Chicago Podcast Network. So, we've talked about the process of building the JWST and the solar shield in particular, but once it's all built and tested, you just have to send it up into space and hope everything goes according to plan.
No matter how many times you practice with that parachute, it comes down to the last time you pull that ripcord, and that all depends on how you packed it.
Oh, that is a lot of pressure. And I know it's not the same, but it kind of feels like how I spend like 5 days a week for 2 months straight working on the same music with my students, only for them to perform once for 10 minutes.
Lower stakes, huh?
Depends on who's asking.
Yeah, I just remember the nerves that I'd get from something like my grade school egg drop. But this was years, nearly a decade of work and more money than I have ever seen in my life. I assumed that Mike would be nervous as hell during the launch.
When you're in a high pressure situation like that, you focus on your work, on your job, and you just kind of put blinders on and you try not to think about it. And then when you look back at it and you say, Jesus, how did we do this? But when you're in the mud, when you're in the thick of it, you're just trying to do your job. And that might be the only thing that keeps you from going insane, because there wasn't much we could do, but we did have some contingencies that we worked out. We didn't want to do them.
Maybe I missed this, but when did the JWST launch again?
So the satellite was launched December 25th in 2021, Christmas Day, but they didn't finish deploying all the moving parts until January 8th. And it wasn't until Groundhog Day that they were able to focus those 18 mirrors of the telescope to start actually looking and taking pictures.
That's quite the long process. I guess I assumed it was all just a one and done kind of situation.
Well, just remember those tennis court-sized solar shield sheets. You want to make sure that they get pulled out without tearing or catching on anything. And Mike compared the whole size of it all to an observatory in California.
It's bigger than Mount Palomar. If you realize, it's the biggest telescope that's ever been put into space. It's about, 6 times more collecting area than Hubble.
Yeah, okay, I guess like a huge moving contraption takes time to actually unfold. Speaking of which, why do we even need these telescopes like JWST or Hubble to be in space? Don't we have enough flat land in like Arizona or something where we could just use a huge mirror array that we could actually service?
Well, we do have plenty of observatories located here on Earth. McDonald Observatory, for example, is out in West Texas where there's less light pollution. And of course, there was the Arecibo radio telescope that was in Puerto Rico before it got wrecked by a hurricane.
Exactly. So why don't we have more of those?
Well, there are a lot of drawbacks to being on Earth.
The telescopes on the ground, if they want to see certain wavelengths in the infrared, well, they're looking up through an ocean of air with a mess of water in it. That light gets absorbed.
That's right. You mentioned that JWST was infrared, but I have to ask once again, why? Why that particular wavelength? Isn't Hubble looking at a different frequency?
Right. Hubble uses visible light for its telescope, and it's gathered us some really incredible images over the years. But having JWST use infrared actually allows us to see further away and therefore deeper into our universe's past.
If you think about, our universe is expanding, right? Most people would have heard that before, which is a funny thing because it's not like the galaxies are moving away from each other. The galaxies are standing still. It's the space between them that's multiplying like the hairs on your head. It's just getting bigger and bigger and bigger. So what that does is as light travels through a universe that's expanding, if that light starts out as blue shortwave light, and they believe most of the first stars in the universe were very hot, very blue. And that's what we're looking for. That shortwave light, as it travels through a universe that's expanding for 13 billion years, gets stretched out like a slinky. By the time it reaches us, it's no longer shortwave blue light, it's long-wave infrared light. And it gets so long that the first galaxies, that light has redshifted so much, Hubble and a lot of the ground-based telescopes couldn't see it. So you need a big infrared telescope that's out in space to see this stuff.
Oh, that's fascinating. Lots to unpack here. First, the light we're observing had to travel great distances to get to the telescope, which means that we're basically looking into the past. We're seeing those objects as they were millions of years ago when the light was first emitted, kind of like a much more exaggerated video delay. Second, you're also saying that the light itself changes as it travels because the space it's traveling through is expanding?
Yeah, basically the light shifts frequency as it moves through space. I actually have a friend who in college dressed up as a sexy redshift and had the physics equation written across her arms.
Well, I do love a good niche costume. Anyway, because the JWST's huge array of mirrors can pick up on infrared light, we can see even further into the past, which then translates into some beautiful images I've already been seeing online.
Oh yeah, I've seen some incredible images too. Mike mentioned one in particular to me as well.
You've probably seen that image that it has little gravity arcs in it from the gravity lensing it. When that came out, my wife saw it and she looked at me, she goes, looks just like Hubble. And then the truth is, it does. But what people don't realize, and the press didn't really do a good job on this, yeah, it looks like Hubble. The Hubble picture took 14 days. We did that in 12 hours.
Oh, so this telescope can also collect images much more quickly?
And we're still in the early days too. When I spoke with Mike late last year, he explained that they still haven't really given it full throttle, so to speak. We haven't really run the much longer exposures across multiple days to see what we can discover. And I should mention that while the mirror array is the most obvious scientific tool aboard the JWST, it isn't the only one. NASA added several tools with the expectation that JWST's mission would last at least half a decade.
The requirement was 5 years, and they wanted 10 years worth of fuel. So, I mean, I used to argue with people about this. The people would say, "Oh, make it more fuel, more fuel." And I'm like, the average science instrument doesn't last 10 years. It lasts around 7 years. A good one might last 10 years, but, So as it turns out, we put 10 years of fuel on Webb because the Ariane rocket gave us such an accurate launch, and we didn't use much fuel to correct its trajectory. We have over 20 years of fuel on board. Do I hope I'd love Webb to last that long? But the truth is, science instruments, filter wheels, parts that move, I think at the end of 10 years, we have 4 science instruments on board. At the end of 10 years, maybe 2 of them will still work, 2 or 3. But, we'll be limited not by the fuel, but by the life of a science instrument. And hey, I'd be the first one to love to say Webb will be up there for 20 years working. And I'm still working Webb. I'm still the lead engineer. So I'm doing everything I can to make it last for 20 years.
Man, stories about space research always feel so inspiring and exciting.
And I'm an unabashed nerd myself. I grew up looking at the stars with my dad through his telescope and watching episodes of Star Trek Next Generation or Voyager. I kind of expected Mike to have a similar origin story to his love of space.
Well, first I was a Trekkie, okay? I mean, I grew up, I was in the 60s, and so I saw the original Star Trek with Captain Kirk and all that, and that was fun to watch.
Oh yeah, with Voyager?
No, it's Enterprise. NCC 1701.
I don't know anything about this.
But I was a child of the space program. And then I just grew up watching the space, the race to the moon, which for me was better than any damn science fiction, because, the drama and the drama of that was enough to keep me entertained till I was 9 years old when I saw Neil Armstrong walk on the moon. Then shortly after that, we witnessed the drama of Apollo 13. And, so I kind of like science fiction to a degree, but I think that, in reality, it was the space program itself that, that entertained me or kept me, that's what I was most interested in.
I get that. It's like seeing science fiction happen in real life.
I mean, I'm still a Trekkie, but there is something even more inspiring about seeing real people go into space and rely on these crazy feats of engineering to survive up there and conduct some seriously cool research experiments.
I hope that JWST helps inspire the next generation of scientists and mathematicians in a similar way.
Me too. I mean, we're still in the early days and we're already getting such beautiful images.
I'll tell you that the image that just surprised me, it isn't really scientifically revealing, but I loved it, was that image we just took of Neptune. The rings of Neptune were really, we knew they were there. We knew that, in fact, I think when it was discovered, someone said it's probably a partial ring. Well, Google it, because you'll think you're looking at Saturn. Oh, it's the most magnetic. It's my favorite of the pictures so far.
Besides pretty pictures, did Mike have a particular scientific question he was looking forward to answering?
Webb was called the first light machine. He was going to see the first light that turned on in the universe. And I'm really, that's what I'm probably most interested in.
First light in the universe. That is a lot.
I know. We're really going to have to keep our eyes open for all the incredible new discoveries and unexpected findings that JWST brings us. And every time we see something in the news, we can remember all that incredible engineering
and math
that went into making this new telescope possible. And don't forget to check out our show notes in the podcast description for more on the building of the JWST and further resources on the mathematics and statistics behind we get such inspiring images from space.
And if you like the show, give us a review on Apple Podcast or Spotify or wherever you listen. By rating and reviewing the show, you really help us spread the word about Carry the Two so that others can discover us.
And for more on the math research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. We're also on Twitter at IMSI_institute, as well as Instagram at IMSI.institute. And that's IMSI spelled IMSI.
And do you have a burning math question? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us? Send us an email with your idea.
You can send your feedback, ideas, and more to sadiewit@imsi.institute. That's SADIEWIT at imsi.institute.
We'd also like to thank our audio engineer, Tyler Damme, for his production on the show. And music is from Blue Dot Sessions.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We're supported by the National Science Foundation and the University of Chicago. All right, you ready?
Yeah, let me just have 10 more bags of chips and I'm ready to go.
Chips. The satellite was launched December 25th in 2021.
Merry Christmas.
Merry Christmas.
Merry Christmas.
All right, Flat Stanley. Oh, no, sorry, Flat Margaret.
Flat Margaret. Oh, God.
Deep cut. A podcast from the Institute for Mathematical and Statistical Innovations. I said that plural.